Dear students, today I am going to begin the chapter Magnetism and Matter, one of the easiest chapters in class 12 physics. I think you might have seen magnets of different sizes and shapes. For instance, a bar magnet, which is like this, or a horseshoe magnet. It is more or less like this. Or in some electrical devices, in some electrical instruments such as a transistor radio or in amplifiers, you notice magnets which are in the form of short cylinders. Okay. That is, magnet is a substance which attracts ferromagnetic materials like iron, nickel, cobalt, steel, etc. They exert some influence on other magnets or magnetic materials. Such substances are called magnets. These magnets are classified into two types: natural magnets and artificial magnets. Fe3O4 magnetite, which is available in nature, is known as natural magnet. One can convert certain types of materials called ferromagnetic materials like iron, steel, cobalt, and few alloys like alnico into magnets, and they are called artificial magnets. These artificial magnets are further classified into two types: that is, temporary magnets and permanent magnets. Okay. So there are different types of magnets: natural magnets, artificial magnets. Artificial magnets are further classified into permanent and temporary. So though there are different types of magnets, basically a magnet is a magnet. It possesses few important characteristic features. One of them is its attractive property. Take a bar magnet and dip that bar magnet in iron filings and lift it up. You notice most of the iron filings, they cling, they get attached at the ends rather than in the mid portion. This shows that the ability to attract ferromagnetic materials is mostly concentrated at the ends rather than at the mid portion. These ends are called magnetic poles. We consider two imaginary points inside the magnet nearer the ends where this attractive property is assumed to be concentrated. These two imaginary points inside the magnet nearer the ends where this attractive property is assumed to be concentrated are called magnetic poles. The distance between these two magnetic poles is called magnetic length, and it is generally identified with 2L rather than with the letter L. Here magnetic length is identified with the letter 2L. Later we will discuss the reason for identifying magnetic length with the 2L rather than with L. The distance between these two faces of the magnet, it is a physical length. But clearly it is evident that magnetic length is slightly less than the physical length. This magnetic length 2L, is nearly 5/6 that of the length of this bar magnet, the physical length. What I mean by this physical length is the distance between these two faces of the bar magnet, or it is approximately equal to 85% of the physical length. For instance, if you consider this as a bar magnet, and if the distance between these two faces is 12 centimeters, that is the physical length is 12 centimeters, then its magnetic length is 5/6 of 12, that is 10 centimeters. So magnetic length 2L is taken to be 10 centimeters. Similarly, the length of this, the physical length of this magnet is 18 centimeters, then its magnetic length is 15 centimeters. Or one can pose the question the other way around. If the magnetic length is 12 centimeters, what is the physical length? So physical length is 6/5 times that of magnetic length. So if the magnetic length is 10 centimeters, 6/5 times 10, that is 12 centimeters is the physical length. Okay. So one of the important properties of this magnet is its ability to attract magnetic materials is mostly concentrated at the two ends. There are two imaginary points inside the magnet nearer the ends where this attractive property is supposed to be concentrated. These two imaginary points are called magnetic poles. The distance between these two poles is known as magnetic length, which is nearly 5/6 or 85% of the physical length. And another property is directive property. Take a bar magnet and suspend it freely by means of a torsionless string. Then, whatever may be the initial orientation of this magnet, it finally comes to rest along Earth's north-south direction. The end which points Earth's north is taken as north pole of the magnet. The end which indicates Earth's south is taken to be the south pole of the magnet. This is how we name the two poles of a magnet. Whenever a magnet is freely suspended and under equilibrium, the end which points Earth's north is taken to be north pole of the magnet, and the end which indicates Earth's south is considered to be the south pole of the magnet. Later, while discussing terrestrial magnetism, I will explain you the reason for this nomenclature, why this end which points Earth's south is taken as the south pole of the magnet, and the end which points Earth's north is considered to be north pole of the magnet. So this is directive property. That is, every freely suspended bar magnet in the horizontal plane always comes to rest along Earth's north-south direction. This is the principle we use in magnetic needles or compass. Okay. Whether you are traveling in a jet plane, even though it is a plane with state-of-the-art technology, or a ship, finally, in order to find the direction of motion, you have to rely on this compass needle. Okay, this is one property. Next, let this be a bar magnet. Say one end is north pole, the other end is south pole. If you cut this into two parts, either unequally or equally, that doesn't matter. If you cut this into two parts, then this end continues to act like north pole and this end acts as south pole. And this newly formed end now behaves like north pole and this end acts as south pole. If you further cut this into two parts, either equally or unequally, this end still continues to behave like south pole and this end acts as north. So if you cut this magnet into a large number of pieces, each piece, however thin it might be, one of its faces acts like north pole, the other face acts like south pole. In other words, it is impossible to isolate a pole from a magnet. Or isolated magnetic poles do not exist in practice. But while explaining few concepts, we consider isolated magnetic poles. They are only hypothetical, they are theoretical assumptions. But in practice, isolated magnetic poles, they do not exist. So when you cut a magnet into a large number of pieces, and every piece behaves like a magnetic dipole, that is, one of its faces acts like north pole, the other face acts like south pole. It is impossible to separate a pole from a magnet, or isolated magnetic poles, they do not exist. Next, another one is, like poles repel each other and unlike poles attract. For instance, you take two bar magnets, arrange them like this. They are arranged, say, coaxially, with these two ends like poles, north poles. Then these two magnets show a tendency to move away from each other. That is, there acts a force of repulsion between them. If you reverse one of the magnets so that their unlike poles are nearer to each other, then they show a tendency to move towards each other. That is, there acts a force of attraction. So this clearly proves that unlike poles repel each other, unlike poles attract each other, and like poles repel. Like poles repel each other and unlike poles attract. But repulsion is considered to be the shoe test for magnetism. What I mean by this is, you are asked to find whether this is a magnet. If it is a magnet, you are asked to find which end acts as north pole and which end acts as south pole. You are provided with a bar magnet. Now naturally, you place this piece of material given to it closer to the bar magnet. If you notice, this material is being attracted by this magnet, to what conclusion you come? Can you say that this is a bar magnet with this end acting as south pole and this end acting as north pole? There is a possibility for that. This can be a magnet with this end acting as south pole and this end acting as north pole. Or this is a ferromagnetic material, such as a piece of iron. It might be a piece of iron. Then this, being the ferromagnetic material, it gets attracted by the magnet. So because this material is attracted by a bar magnet, you cannot jump into the conclusion that this is a bar magnet with this end acting as south pole and this end acting as a north pole. It could be a ferromagnetic material. On the other hand, nearer to this bar magnet, the given material is placed. We don't know whether it is a bar magnet. If it is repelled, strongly repelled by this bar magnet, then you can definitely say that this is a bar magnet with this end acting as north pole and this end acting as south pole. Okay. So though like poles repel each other and unlike poles attract, repulsion is considered to be the sure test for magnetism. Okay. This is one more important property of a magnet. And another one is, you take a bar magnet and place a ferromagnetic material such as a piece of iron close to this magnet without any actual contact between them. Then you notice that this piece of iron getting attracted by this bar magnet. It clings to this and gets attached to this. Okay. But what actually happens before this attraction takes place is, when you place a ferromagnetic material close to a bar magnet, even though there is no actual contact between them, this magnet induces magnetism into it in such a manner that this end acts like an unlike pole and the farther end acts like a like pole. That is, this bar magnet, even without any actual contact with this piece of iron, it induces magnetism into this ferromagnetic material so that it starts behaving like, it starts acting like a magnet, with the nearer end acting as an unlike pole and the farther end acting as like pole. So now, because of this, because these two unlike poles are nearer to each other, this piece of iron gets attracted by the magnet. It gets attached to this. This property of inducing magnetism into a magnetic material, even without any actual contact, is known as magnetic induction. So these are the important properties associated with the magnet. One is, it's an attractive property. Every magnet possesses two poles where the entire attractive property is assumed to be concentrated. The distance between the two magnetic poles is known as magnetic length, and it is generally identified with the 2L. Next, directive property. A freely falling bar magnet always comes to rest along Earth's north-south direction. The end which points Earth's north is called north pole of the magnet, and the end which points Earth's south is called south pole of the magnet. And third, it is impossible to isolate a magnetic pole from a magnet. In other words, isolated magnetic poles do not exist in practice. They are only theoretical approximations only. Okay? And another one is, like poles repel each other and unlike poles attract. But repulsion is considered to be the sure test for identifying magnetism in a material. And finally, a magnet induces magnetism into a magnetic material even without any actual contact. This is known as magnetic induction. We will discuss few more important concepts related to magnets in the next session.